Started. So welcome everybody. Thank you for joining us. My name is Kaylee Allen and I'm the EBICS Education and Diversity Programs Manager. And I'm also the Program Director for the BEAM program. Allison Young, who you've heard speaking, is our extraordinary BEAM program assistant. And she's also a program assistant inside of the Center for EBICS. So first and foremost, I want to thank everyone for joining us in celebrating our 2021-2022 BEAM interns. They have completed their 10-week summer research internship. And so today we are going to provide each one of them an opportunity to share with us what their experiences were for this summer. So just to kind of give you a little bit of background about what BEAM is, in case you are new to the program. BEAM is a year-round paid high school science education and research program. This program is designed for juniors and seniors from underrepresented or marginalized groups, not just within Cambridge. We now have partnerships with Cambridge Ridge and Latin, Phillips Academy in Andover, Greater Lawrence Technical School, the Community Charter School of Cambridge, Prospect Hill Academy, the Boston Collegiate Charter School, and the Boston Arts Academy. So our partnership is really starting to expand, and we're hoping in the coming years to have interns from each one of these schools. Not only is our cohort expanding each year, but that means that the labs that are participating in the BEAM program are also expanding. So we this year have 7 interns, and therefore we have 7 labs. So I want to take a quick moment and thank Professors Van Rees, Professor Cole, Gao, Henry, Weiss, Cam, and Shalak for hosting BEAM interns this year. And then also I'd like to take a moment to thank all of the graduate students or postdocs who are their mentors. Without our MIT professors and our MIT graduate students and postdocs, this program certainly would not be as successful as it has been for the last 3 years. So definitely want to take a moment and give each one of those individuals a round of applause. And thank you for everything that you're doing to expand and diversify student participation and retention in STEM by exposing these fabulous interns to bioengineering, chemistry, mechanical engineering, physics, and all sorts of other laboratory techniques. So thank you very much, everybody. So this year's interns are 7 students. And so here we have 3 of them. So on the left-hand side, I'd like to introduce you to Astrid. She is a graduating senior at Cambridge Ridge and Latin High School, and she is working with Professor Ron Weiss under the mentorship of Noreen and Catherine. Here in the middle, we have Daniela, who is from Greater Lawrence Technical School. She is a rising senior this year. And she has been working with Professor Roger Cam under the mentorship of Marie and Yorgis. And here we have Mohammed, who is I believe he's actually a junior, not a senior. Well, I guess rising senior, right? He'll be a senior next year. And Mohammed is also from Cambridge Ridge and Latin High School. And for this past 10 weeks, he has been working with Professor Van Rees under the mentorship of Lingbo and Jingjae. And then here we have our other 4 interns who are part of our program. So Erin is from Phillips Academy, and she is a junior working in Professor Mingao's lab under the mentorship of Yu Long and Wen Wei. And then we have Hannah, who is from Cambridge Ridge and Latin. She is also a junior and is working with Professor Matthias Cole under the mentorship of Ben and Hannah. And we have Lucy Engles, who's a junior from Cambridge Ridge and Latin High School, working with Professor Ashe Henry under the mentorship of Kirash. And then we have Mariela Allen-Cadet, who is also a junior from Cambridge Ridge and Latin High School, working for the last 10 weeks with Professor Alex Shalak's lab under the mentorship of Sam and Mike. So again, I want to give a special thank you to all of our PIs and mentors, and then also a special thank you to each of these high schools for promoting the program and for increasing our participation in the BEAM program. And so without any further ado, we'll go ahead and get started. So the order that we're going to have today, we will begin with Daniela, who is going to talk with us about her breast cancer research. And then we will move to Hannah, who is going to talk with us about a musical color synthesizer, which is sort of an interesting bio-inspired material. And then Mohammed is going to speak with us about flow trapping and Reynolds numbers. Lucy then will talk with us about heat transfer across semiconductors. Astrid will discuss with us her continued research. So Astrid was a junior last year and was part of the BEAM program. And so this year she was continuing her research inside of the Weiss lab. And so she'll talk with us about oscillators in mammalian cells. And then Mariela will discuss with us about the research that she's been doing in the Shellac lab on fluorescence microscopy. And then Erin will wrap it up talking about how cell shape can change through tessellations. And this is the work that she's been doing in Professor Ming Gao's lab. So I'd like each of you to just take a moment and kind of look at the diversity, not only within our students, but also with the science that they're doing. With them having to be completely virtual this summer and probably completely virtual in the fall, our mentors and PIs have done a really good job at finding research that can keep the students engaged, as well as provide them very unique experiences. So I'm very excited today to get to have all of the interns share with you the research that they've been doing for the last 10 weeks. So we will get started just now with Daniela, who will be giving her presentation on breast cancer cell extravasation. So I will stop sharing my screen, Daniela, and then you are welcome to share your screen and unmute yourself. At the end of each presentation, our interns will accept some questions. You are welcome to unmute yourself and ask a question. If you do not wish to unmute yourself, you may put any questions that you have in the chat, and Allison and myself will make sure to field them to the speaker. So thank you. Whenever you're ready, Daniela.
Hello, my name is Daniela Paulino. I'm an intern in the BEAM program in the Roger Chem lab. And this is my presentation on using microfluidics to model breast cancer cell extravasation and Alzheimer's disease. The contents of these templates. So first, we're going to start with some background on breast cancer metastasis, Alzheimer's disease. Then we will be talking about a microfluidic pump. And then I will be talking some things about MATLAB. So breast cancer cell extravasation. Breast cancer is a disease that is a result of mutations or normal changes in the genes, which cells grow out of control. This is a picture of the structure of a normal cell and a cancerous cells. So if you can take a moment to look at it, you will notice that there are some differences in them. Some of the differences is the cytoplasm. In the normal cell, you can see that the cytoplasm is more rounded and is more thick, while in the cancer cell is more thin and is not that rounded. Some other changes that you can see in the picture is the nucleus. In the normal cell is again like really rounded, and in the cancer cell you can see that it has a weird shape, and you can also have two nucleus per cells. Next slide. So causes of breast cancer. Breast cancer can be caused by a lot of things, but some of the most important reasons why somebody can have breast cancer is because of a family history, gene mutation, late childbearing, so having a child after 30 years old and older, that can increase the chances of getting breast cancer, early menstruation. There is when you have early menstruation, you have higher exposure to estrogens. Estrogens is a hormone that promotes development and maintenance of the female characteristics. Some signs and symptoms of breast cancer can be a visible lump in the armpit, in the breast, and pain and bloody discharge. Something to keep in mind is the breast cancer can only be diagnosed by a doctor. Next slide. So type of breast cancer. There's quite a lot of types of breast cancer in general, but these are the four main type of breast cancer. So we have carcinomas. They are the most common type of breast cancer. There's that in the lining tissues and organs in the side of the breast. We have the in-situ breast cancer, which is those that have not spread to the surrounding tissue of the breast. That makes them more easy to treat them. The third type of breast cancer that we have right here is metastatic cancer. Metastatic cancer is when there is a primary cancer is located in the breast, but a secondary cancer can happen in these areas of the body, which will only be the lungs, bone, liver, and the brain. Recurrent breast cancer, which is when a patient is free of that disease for a long period of time and the disease comes on again. This picture that is right here, you can see that this is the anatomy of the breast. So most of the time, breast cancer will start here in the levels of the breast. And this over here is basically how the cancers evolve, basically. So we have here the normal cells of the breast. And then this is when EBGLs is starting. So this is basically the abnormal cells growing. Then we have in-situ breast cancer, invasive, which is the malignant part right there, and then metastatic cancer. That's when the primary cancer goes and to form a secondary cancer, which I will talk later on. Next slide. So cancer metastasis. Cancer metastasis is the process that it has to follow according to the metastatic cancer in general. So there is a process for the secondary tumor to grow, and here in this picture, you can see that this will be the primary tumor site, so the primary tumor. And that there is a variety of steps that needs to happen for the secondary tumor to grow. So the first step is invasion and migration. So invasion and migration is the direct extension and penetration by cancer cells into the neighboring tissues of the breast. Then we have extravasation as the second step. Extravasation is when Intravasation is when the invasion of cancer cells to the blood and lymphatic vessels. Then we have circulation, and then we have extravasation. Extravasation for me is the most important step. In extravasation is basically the secondary site to form the cancer tumor. So in extravasation, a process called mesenchymal epithelial transformation goes on. This process allows the cancer cells to form the secondary tumor in general. And the last step would be colonization. Colonization is when the cancer cells colonize the secondary tissue to eventually form the metastatic tumor. Next slide. So now we're going to talk a little bit of Alzheimer's disease. Alzheimer's disease is a brain disease that causes trouble with memory, thinking, and behavior. If you can see this picture right here, this is a difference of a healthy brain, and this is a baby with severe Alzheimer's disease. So we have a lot of proteins in the brain, but some of those proteins are amyloid beta, which is a protein fragment, and tau, which is a protein. And we also have plaques and tangles in the brain. The plaques and tangles are the prime suspect of damaging and killing nerve cells, which will eventually lead to Alzheimer's disease. The problem with the amyloid beta in the tau is that amyloid beta deposits the plaques, and tau are basically the fiber tangles of the tangles are basically twisted fiber of tau in general. So here you can see in this picture right here that this is the normal, how a normal brain looks like, and this is the brain with Alzheimer's disease. So you can see the tangles, and these are the tangles, and this is where they are located. The amyloid beta protein fragments, they build up in between the spaces of the nerve cells, and tau protein help stabilize the internal skeleton of the nerve cells, so they are like inside the nerve cells. But we have amyloid beta, which are deposits from the amyloid, which deposits the plaques, and tau, which deposits the tangles. So these are the tangles, and these are the tangles, the plaques and tangles, and they basically just go around the brain, killing and damaging the nerve cells, which again will lead to Alzheimer's disease. Next slide. So these are the pictures again of a brain, of a healthy brain in a brain with Alzheimer's disease. So you can see that the cortex, the cerebral cortex here, is more thick in the normal brain, but in the brain with the Alzheimer's disease is more thin. Another thing is Alzheimer's disease most likely affects the front lobe of the brain and the temporal lobe of the brain, because we know the Alzheimer's disease basically affects thinking and behavior. The frontal lobe, which you can see right here, affects movement, intelligence, reasoning, behavior, memory, and personality. The temporal lobe of the brain affects speech, behavior, memory, hearing, vision, and emotions. Next slide. So cell extravasation and Alzheimer's disease, they're really different. So cell extravasation is part of a cancer metastasis. It can only happen in the cancer disease, and this will eventually lead to form a cancerous tumor. And Alzheimer's disease is the most common cause of dementia. It affects thinking and behavior, and is most common at 65 years old and older. But both of these diseases have something in common, that is the flow of them. So the cancerous cells have a flow which they follow through the lymphatic vessels and the blood vessels, and Alzheimer's disease has a flow in which the plaques and tangles follow, in which they are cleaning the brain. Next slide. So a microfluidic pump. Right now, I'm using a microfluidic pump. You can see the picture right here. This is the microfluidic pump. This is the pumping chamber, the valve, and the capacitor. So we're using a microfluidic pump to reach our goals. So our goal is to mimic the flow of the cancer cells in the blood vessels and the lymphatic vessels in the lymphatic system, And we want to mimic the flow of plaques and tangles in the brain too. So to mimic these flows, we are using a microfluidic pump. Friendly reminder is that plaques and tangles are the prime suspects of damaging and killing the nerve cells in the brain, which again eventually lead to Alzheimer's disease. Next. So again, this is the microfluidic pump, which is connected to another device, which is right here. This image right here, it shows the microfluidic pump. And here, this is a device in which is the microfluidic pump is attached to. So here, this is the pressure input. So here we have to add a pressure so the liquid in the microfluidic pump go through. From when we want to we want to mimic the flow of the cancer cells through the lymphatic vessels and the blood vessels, we will use jelly bits to mimic the cancer cells in the microfluidic pump. So for the microfluidics in general and the bits to move, we need to have some pressure. So this is the pressure input. Then the fluid will begin flowing this way over here. Then it will eventually go to the device. And here there is the microvascular network in which the fluid will pass by, and it will go through again, and it will just keep rotating around. So MATLAB. I'm using MATLAB to figure it out the amount of pressure that it has to be added in the microfluidic pump. So MATLAB is a software. The developer of this software is MathWorks. It was designed by Cliff Muller, and it was first released in the late 1970s. Next slide. So these are some of the data that I have gotten from MATLAB in general. So the pressure that I added in this picture was 1,300 pascals, and the period in seconds was 1. So in 1 second, we will add the 1,300 pressure in pascals, then the other second, the pressure will not be added, then the next second, it will be added. So this is the data that I got. So you can see that the line is kind of pretty clear how it goes up and then it goes flat right here. And in here, it kind of changed. So here it was the same amount of pressure in pascals, so 1,300, but the period in seconds, it changed. So instead of being 1, I changed it to 5 in here. So you can see that this is kind of, is really different from this one right here. So the fragments are like going up and down, up and down, up and down. And I wanted to like figure it out what was the like that dramatic change in it. So I did some more data in it. And right here, this is the data, the other data that I tested. So I changed the pressure. Instead of being 1,300, this time it went up by a bit. It was 3,500. And in the first picture that we have right here, the period in seconds is 1. So again, you can see that the line is pretty clear in general how it goes up. And then I put the same amount of pressure, but with different seconds. Instead of being 1, I put it into 3. And now we can see that there is quite like, the line is not so clear. So we can see that the line goes up and down, up and down, up and down, up and down until the top right here. And then I added 3 more seconds, which makes them 6. So I did again the pressure in 3,500, and I added 6 seconds in the period. So this is how the data showed. So you can see clear the up and down, up and down, up and down in the data right here. So this is the end of my presentation. I would like to say thank you to the BEAM program, the emerged behaviors of integrated cellular system, the National Science Foundation. I will also would like to say thank you to Professor Roger Kam, Ms. Alison Young, Dr. Kelly Ellen, my mentors, Gorgeous and Marie, for everything, for helping me get through this summer term. And yeah, thank you for listening. Is there any questions or comments that I can answer?
Great job. Thank you very much.
Thank you.
We have time for maybe 1 or 2 questions. You can feel free to unmute yourself or to enter it in the chat. I'll keep an eye on the chat. I see Matthias, you have your hand up.
Yeah, nice presentation and really sort of impactful topics and positioning is within breast cancer and Alzheimer and seeing the interface between them and how you can study sort of the flow behavior of these cells and maybe make inroads in both problems is quite fascinating. In your data that you showed, the change in the flow profile as a function of the period of pressure on, pressure off, I assume that is right. Are you modeling the physiological behavior because of the pulse rate of a human, like where you would have a beat every second or every 5 seconds or something like this? And what sort of do you expect to happen when you go to too slow pulse rate? Does the oscillation do something for the cells in terms of making them extravasate better or worse?
Thank you for your question. I'm trying with the data. Basically, we're trying to kind of figure it out. Which speed we should put in the microfluidic pump. We are still doing research in it. So we need to, one of the things that we need to figure it out is basically how it works in the human body. But I think that the pressure that you were talking about, I think that it depends on like the person, the patient, and it depends on the stage of like the disease in general for the like the pressure when it comes and it goes in general, if that answers your question. But we're still doing some more research, so I hope to figure that out, which is the exact pressure in each stage of the diseases.
Very cool, thank you.
Great. Well, thank you very much, Daniela. That was a wonderful presentation. So one last round of applause. Yeah. All right. And our next speaker is going to be Hannah Chun. Whenever she has her presentation pulled up, she's more than welcome to unmute herself and get started.
Okay. Hello, my name is Hannah Chun, and for the past few months, I've been interning at the Matthias Cole Lab. The title of this project is Musical Color Synesthesia, a touch-responsive, bio-inspired photonic synthesizer, and today I'll be telling you more about it. Before we get into anything, I'm going to define what a synthesizer is because I'll be using this word a lot. A synthesizer is any electronic device that produces sound or music. They typically come in the form of a keyboard. So here are a couple examples of what a synthesizer looks like. Next, I'll show you two videos demonstrating the material my lab is working with so you can get an idea of what it looks like. So as you can see, changing the amount of pressure that you apply to the material changes the color. The first part of my presentation are the lab objectives. Our goal is to create a unique synthesizer that uses color-changing, stretchable materials to turn visual patterns into sound. This synthesizer will have newer features than most, and it will allow the user to express their full creativity with it. Our synthesizer also reflects natural phenomena. Standard musical synthesizers often have a boring and technical look, which can discourage users from using them. Through the inspiration of biology concepts, the one we're making will change that. This is a great example of how art and science can go hand in hand, and why the A in STEM exists. The second part is the background theory. The synthesizer is made of a unique film-like material that is based on the concept of thin film interference. Thin film interference is a natural phenomenon where light reflected by the boundaries of a film interfere. This is often seen in things like the rainbow and soap bubbles, as shown in the pictures to the right. We're also using image processing by working with something called OpenCV, which stands for Open Source Computer Vision Library. This is a library of different programming functions that can allow a user to process images in a variety of ways. For example, an image can be changed to have a grayscale color scheme, or it can be blurred or have a border. So here on the right, you can see that there's an image of like this dog, and then this is the original image. And using OpenCV, you can kind of modify it so it like has a filter like this. Structural coloration is when color is produced through microscopic structures that interfere with visible light. So here is a photo of peacock feathers, and the unique colors on a peacock's feathers are actually a really great example of this. An elastomer is a polymer or a molecular structure made of similar units throughout that has weak intermolecular forces and viscoelasticity. In other words, it's a rubbery material, such as a rubber band, that is malleable but returns its original shape when it's not being stretched. And then the RGB color model is a very commonly used color model. RGB stands for red, green, blue. By combining a certain amount of each of these three, a variety of different colors can be produced. Finally, HSL and HSV stand for hue, saturation, lightness, and hue, saturation, value. These are alternate representations of the RGB color model. Here are the equipment and components that we're using. Some of the software and equipment we're using include OpenCV, Python 3, and Visual Studio Code. However, this is a long list of unfamiliar terms, so I've added visuals on the next slide to make it easier to interpret. On the computer, we're using Python, Visual Studio Code, OpenCV, and Tinkercad. We're also using the stretchable sheets, as you can see here on the right. At the bottom right is an idea of what the final product will look like. It may not look exactly like that, but it will involve all of these components: the film, a camera, a computer, and a speaker. Now I'll be showing some early designs and drafts of the synthesizer. The first design resembles a keyboard. This would be the most straightforward way to make the synthesizer. Each color would correspond to a different note, like on a real piano, and a camera would pick up the color changes and play different sounds depending on the color. The second design is a square sheet partitioned into 4 equal squares of different colors. Pressing or stretching certain regions would produce a different sound based on the color. The third design consists of a solid base with strips of material placed across, similar to strings on a guitar. The user can press the strings, pluck them, and pull them. Also, the solid base would contain a space to insert a camera. So this is a hand drawing of the design. And then here I use Tinkercad, which is a 3D modeling system, to make a design of what the base would look like. The fourth and most recent design is based on that of an accordion. The sections marked in red indicate where the colored material would go. This design combines multiple different functions. On the left, a user can play it like a piano. In the middle, the user can stretch and compress the material. And on the right, the different buttons can be pushed. One of the downsides of this design is that camera placement would be difficult because the design is larger and would move around a lot. The next section is our observations and findings. Currently, we're leaning most toward design 3, as that is the most efficient and effective. We're also continuing to work on the code. Finally, here are our discussions and future steps. We'll continue improving the code and creating more synthesizer designs. We'll also decide on which sounds or notes to play for each color. I would now like to extend my sincerest gratitude to the following individuals. None of this would have been possible without them, and I cannot thank all of them enough for their help and support. Thank you.
Woo, great job. Yay, round of applause. All right, so I will open this up for any questions that anyone might have. I have questions if no one else has questions. So. Let's see, I think Lucy typed in a question. Yes, so it says, how do you envision artists using this? Why would artists choose this over a regular instrument or other synthesizers?
Yeah, so that's a really great question. And the answer to that is that a lot of synthesizers that you see out there right now are very, they have a very like clunky and very like technical and sophisticated look. So they're not really ideal for a user to look at it and go like, oh, I want to express my full creativity with this object. And another thing that we were thinking about when designing the new synthesizer is that a lot of synthesizers have just buttons on them that you press and then it's over. And the reason we're using this malleable, stretchable material is so that users can kind of, they can simulate a more like free-flowing motion using that. And it's a lot more flexible and a lot more creative.
Can you talk a little bit about the code that you're, I guess, writing and sort of what part that plays in this project?
Yeah, of course. So in the code, that's like what we're using to process the images. So that's gonna allow the camera to like pick up the color changes in the material, and then the code will like help us translate that into sound.
Very cool.
There's one more from Astrid.
Thank you, Allison. It says, what are your current ideas for the color sound mapping?
So do you mean like what colors will correspond to what sounds?
I think that's what she's implying.
Okay. Yeah, so actually that's one of our future steps, is to decide if we're gonna have like each color present a different note or a different sound, because there are a lot of possibilities with this design. So that's actually something that we're gonna be planning in the future soon.
Very cool. Well, I know we're all very excited, and hopefully by the end of the year, we'll have a synthesizer we can play with. So that would be pretty cool. So one last round of applause for Hannah. Thank you very much. All right. So next, we are going to hear a presentation from Mohammed. So whenever you are ready, please share your screen and unmute yourself.
Hello, everyone. I hope everyone's doing well. My name is Mohammed, and I'm an intern at the Van Release Lab under the mentorship of Ling Boji and Xinxiji. And we're focusing on flow trapping with a cylinder pair at a low Reynolds number. So just as a little background, the Reynolds number is basically the ratio between the inertial effect and the viscous effect. So for example, some examples of a low Reynolds number liquid, which is what we're going to be working with, is honey, and high Reynolds number liquid would be something like water. So the reason honey is low viscous, low Reynolds number liquid is because the viscous effects take over, and it's a very smooth and laminar flow. So as we can see here on the left, the low Reynolds number are going to be very laminar, very smooth, and very viscous. But something like water has a high Reynolds number and is very turbulent, and it's unpredictable. So we're going to be focusing, or we're going to be working with a low Reynolds number. And some properties of low Reynolds numbers are the scallop theorem. So for example, we see here a scallop, and when it opens its mouth, we can imagine it going to state A, and when it closes its mouth, it's going back to state B. So it's basically saying there's no net movement. It's just basically going to be in the same place. It's not going to be able to move any further. And then we also have time invariance, which basically means that a point of flow will not depend on the past, like the past history of the flow. And now our motivation. So the importance of flow trapping and the experimenting and studying of it is because we have a lot of very useful, very helpful benefits from it. So for example, we have transportation, capturing, and filtration. So transportation is basically when, say you capture a cell inside of a flow, like the recirculation region, which I'll explain later on. So if we look at this picture here, this is sphere which is spinning, and this darker part is going to be the recirculation region. And as we see, when the bacteria or the cell gets inside of this region, it kind of gets trapped in there. And so and when it's inside of that region, it can either be like the recirculation, since it's a flow, is going to be moving, or the sphere itself will be moving. So then we have capturing, which is just how, it's just trapping where it gets the cell or the bacteria and it traps it. And filtration is something which is not like a 100% concrete or like the main focus. It's something more experimental, but it's basically, allowing some cells or bacteria to go through and, holding some back. So our setup is a pair of identical cylinders, which are separated by a fixed distance, which rotate about their center. So basically, using this setup, and they're going to be, of course, we're going to be simulating them using MATLAB in a low Reynolds number fluid. And our goals are to identify and calculate the area of the recirculation region using the numerical integration for two cases: counter-rotating at equal speeds and counter-rotating at non-equal speeds. So some equations which are very helpful to us and which we're going to be using are the Stokes equations. And so we see on the right the Navier-Stokes equation. So this is much more complicated and complex. So, just to simplify it, since it's a low Stokes equation, we're not going to be needing, all this. So this is a simplified version of the Navier-Stokes equation, basically. And this is what we're going to be using. And Stokes equations, and what we're working with is a Stokes flow, which is just a flow with a low Reynolds number, which again just means very viscous, very smooth and laminar. So we're going to be using the numerical method using MATLAB, and we're going to be solving the Stokes flow using a method of regularized Stokeslets in the 2 dimensions. And we're going to be using finding the area of the recirculation region using numerical integration of the curve. So for example, we're going to see the recirculation region in the next slide, but basically we're just plotting the points on a graph, and then so this is just an explanation of integration. So we're going to be plotting the points on the graph and then finding the area under the graph, which will then give us the area of the recirculation region. So here's the anatomy of a streamline. So at the top here, there's a W is a separation between the centers of the two cylinders. So it's 2.5. The angular velocity are represented by omega-1 and omega-2. So angular velocity 1 or omega-1 is equal to 2, and angular velocity 2 or omega-2 is equal to -2. So they're counter-rotating in this case. And just some terms. So the recirculation region, or just to clarify, this blue thing over here, like these blue lines, are representing the liquid. And these circles in the middle here are the cylinders. So these are the two pairs of cylinders, and blue stuff is the liquid, which we're, again, you can see how they interact. So the recirculation region is just this area over here. So we see how, the rest of the fluid is kind of going around it. But then this part right here is very close to the pair of cylinders, and it's recirculating this part. So that's the recirculation region. The stagnation points are these points over here, where there's where the velocity at that point is approaching 0, and it's just a stagnant point still, and there's little to no movement going on there. And so the methods of finding the recirculation region is to find the stagnation point, find the target streamline, and to integrate to find the area. So finding the stagnation point, we can, one of the ways we did it was by finding the point which had the lowest angular velocity on, say, for example, the positive y plane. And so we can assume that x would be 0 since they're going to be kind of rotating at equal speeds for this case. So this case being the counter rotating at equal speeds. So we can assume that the x is going to be 0. So we just have to find the lowest velocity at the y plane. So for both sides, right? And we can see that it's accurate. It's very slight. It's very small over here, but if I can highlight it, there's a little circle. So that's just how we wrote the code to find the stagnation point, and that's just to plot it to make it easier to find, just to make sure it's accurate. So then once we find the stagnation point, we have to find the target streamline. So the target streamline is going to be the boundary line around the recirculation region. So basically, we want to get the whole recirculation region, right? So we can't just choose like a middle streamline. We have to choose. Just to clarify, a streamline is going to be one of these lines over here. So we can't just find like streamline in the middle of the recirculation region. We're going to have to find it from the outside, or the boundary of the recirculation region to make sure that we have the most accurate results. And then using that, we're just gonna plot it on a graph. And of course, there are gonna be some points which overlap, since it's gonna be like a semicircle. So there'll be some points that overlap. So for example, the x value here and the x value here is gonna be the same. So it's gonna be hard to integrate that way. So that's why when we integrate it, we're kind of gonna be flipping it. So it's kind of like this. Instead of like this. Okay, so we're gonna then find the points, integrate it, and then find the area under the line. And so here are some simulations we ran. These simulations were, so when the cylinders were at a different separation, but had the same angular velocity, and CR over here just means counter-rotating. So we here see, so for the first case, right, we're still basically going to be slowly increasing the separation, but we're going to be keeping the angular velocities the same. So it's always going to be, the first cylinder is always going to be moving at 2. And then the second cylinder is moving at -2. And it's not necessarily like 100% defined if it's like meters per second, just like for the sake of the simulation. So then the separation, we're going to be slowly increasing over a range, which is why the number might seem a little weird or like very weird decimals. So because we did it over a range from 2.5 to 10, and the numbers were split evenly. So that's why the numbers are going to be weird decimals. So we can see that basically as the separation increases, the recirculation region also increases. And we can see here that there are 2 methods we used to find it actually. There was the naive way, which is a way of doing integration, but it was the most optimized, the most accurate way. And then we have the ellipse. So ellipse is basically just finding the major and minor axes, and then plotting an ellipse, and then finding the area using the equation to find the area of an ellipse. So we can find that we can see that like it's actually very accurate, the naive way and the ellipse way. And we're still going to be working on finding the 100% accurate way, which is going to be useful in any case, which is using numerical integration. So we can also see here that the major and minor axes increase as well. So this also tells us that the recirculation region is increasing. And now here's the simulation we ran for the same separation at different angular velocities, but still counter-rotating. So this time we had a ratio of 1 to 2. So the separation was 4. So we can see here that oddly enough, even though the angular velocity is changing, the recirculation region is the same. And that's because the recirculation region is independent, is dependent on the ratio of the angular velocities. So basically, I tried it again. We simulated it again with this time with a ratio of 1 to 4. So we can see here it's much different, the recirculation region, compared to here and here. So there's a difference, especially on the left one. So basically, what we found, and this is a comparison. So this is just a 1 to 2 ratio. These are the streamlines, and the 1 to 4 ratio. So even though the numbers are increasing in different, the recirculation region is staying the same, because for counter-rotating and equal speeds case, we found that the recirculation region was increased. It kept increasing as the separation increased. But for the non-equal speeds case, we found that the recirculation region was dependent on the ratio of the rotation speeds. So our next steps in future work. Next, so for the 2D case, we're going to be doing the locomotion of a cylinder pair in a quiescent flow. I believe that's how it's pronounced. And so that basically means that the flow is going to be still, and we're going to be seeing, and we're going to add tracer particles, and tracer particles are like point particles which are going to follow the flow. So we can use that to see, mark how the flow moves. So we can imagine like a cylinder pair moving in a flow that's at rest, and then seeing how the tracer particles move. And then we're gonna be we're gonna be focusing more on the 3D case. So we're gonna be using a pair of spheres and a pair of cones. So over here, we actually have a simulation that we ran in the 3D case. And we can see that this time it was with spheres and not necessarily cylinders. But so this is kind of looking at it from, this is from the side over here. I believe it's from the top. And so basically, we can see here that, the recirculation region, we can see its effect on the side. So we're going to be focusing more on the interaction between the flows and the cylinders, and the 3D case, of course, because those results, even though they're going to be more intensive on our CPU, we're going to be, be careful about how we run those simulations, and which simulations we run in order to find the most important data and the most accurate data, which will be, most beneficial in real life use. I'm sorry. Yeah, so acknowledgements, I'd like to sincerely extend my gratitude and my thanks and my acknowledgements to Professor Van Rees and my mentors, Lingboji and CCG, and Dr. Kelly and Allison for always being helpful, for always being accessible, especially Lingbo with helping me out with a bunch of the stuff, and of course Professor Van Rees for allowing me to this lab. And so thank you for listening. And if you have any questions, feel free to go ahead and ask.
Great job. Good job, Mohammed. Very cool. We certainly have time for 1 or 2 questions. If anyone has any questions? I see that Matthias has his hand up.
Oh, it's really cool work and not easy, I think. Did you know differential equations before you started this?
Yeah, no, the first thing actually that I was doing was kind of figuring out how that all worked. I didn't even take pre-calc, so it was very complicated for me. But with the help of Khan Academy, I was able to kind of understand it and watching a bunch of YouTube videos on it. And Lingbo and CG also helped me a lot with understanding these equations and how they worked. So big thanks to them again. So yeah, that's kind of how I started to figure them out.
Yeah, it's great to hear that you tackled that because it was beautifully presented. It's a nice starter project, I think. And once you handle these equations really well, you can do a lot of cool things. So congratulations to you, but also to Wim and Lingbo and Jinchi. It's pretty cool. Awesome.
Thank you. Thank you for your question.
That's the thing.
I see.
I was going to say we do have a couple questions in the chat, Mohammed. One from Eric. So Eric said, great work. Impressive, especially without having taken diff EQ or even calculus, differential equations. So the question is there anything significant with respect to the rotating cylinders? Do they correspond to something physical?
What do you mean by exactly corresponding to something physical? Because I guess what we were trying to simulate was in a real life experiment, just using a pair of cylinders, since of course we weren't able to go in person and stuff. But is there anything very significant about rotating cylinders? I think that we used rotating cylinders just as a first step for the 2D case, because then we're going to move on to spheres in cones in the 3D case. So I believe that's it's just a very important first step. So yeah, I hope that answers your question.
I was just wondering why cylinders or cones or spheres or anything. Is it are you simulating something? Yeah.
Yeah, of course. Sorry. Yeah, no. So yeah, the reason we're using that is because it's going to be very important in the study of, I believe, things like microfluidics, fundamental engineering, applied engineering and fundamental sciences. And this is because using these things is going to generate recirculation region, which we can then use to trap cells, bacteria, anything we want. And so once we can trap it, it's going to be very important to a lot of the experiments that we're going to be are in those fields. So I hope that's what answers your question, and thank you for the question.
Awesome.
Great. Matthias, would you like to ask another question?
Yeah, I want to. The cylinders, it made me think of these rotor ships, the Flettner rotors, where you rotate a cylinder on a ship and that gives the ship propulsion by creating this Magnus effect type thing. Is that a completely different phenomenon in terms of Reynolds numbers because it's turbulent, or can you also sort of treat some of these phenomena like propulsion with the rotating cylinders?
That's a good question. I believe it's definitely going to be related, of course, because Reynolds number, it affects all liquids and fluids. So, but I think it might be similar too because of the propulsion. So using those, I remember before we were talking about the scalp theorem and how that was just one hinge, how it moves forward and then moves back, just like that movement. But then with the pair of cylinders, I think it focuses more on just like the still movement. So, I'm not sure if that makes it similar, but I hope that answers your question.
Does. Thank you.
Put a link in the chat. There is a good question. And there's really cool behavior at like finite Reynolds number with these things. Because when you go from Stokes flow to inertial regime, they counter rotate. At first, they kind of pull themselves up in the flow. They pull flow around. And then when the Reynolds number increases, they go the other direction because they push flow through the gap and they form a jet and then they turn. So just by dialing up the Reynolds number, like you put the same thing in honey or in air and it will go in different directions. It's a really cool,
Awesome.
cool system.
Very cool. Well, I'm excited to see the progress of the research and going from 2D to 3D and sort of see where this goes. So very exciting stuff. Thank you very much, Mohammed, for sharing your progress over the summer with us. The next speaker is going to be Lucy Engles. So whenever Lucy is ready to present, please share your screen and unmute yourself. And by the way, I love your background.
Thank you. New York is my home away from home. So this summer I've been in the Henry Lab doing research under the guidance of Kirash Gordiz. My project title is Data-Driven Investigation of Heat Transfer Across Semiconductor Interfaces. I'll talk through basically everything that's mentioned in that title, starting with semiconductors. So you might have heard of a recent semiconductor shortage due to the pandemic. That's one way semiconductors have been in the news. Well, these semiconductor chips are made out of semiconductor metals. Semiconductors have a conductivity in between conductors, such as copper, gold, and silver, and insulators, such as wood, glass, and plastic. The semiconductor chips in electronics are made out of these semiconductor metals, more specifically semiconductor compounds, which are made out of a combination of different semiconductor metals. As I've talked about, semiconductor chips are used in many different types of electronics, and therefore semiconductor interfaces are vital for the performance of electronics. So electrical systems in computers have billions of electronic chips or transistors made out of the interface of semiconductor compounds. And all of these semiconductor interfaces generate heat. An optimized electrical system will limit the production of this heat. So why do we care about that? Why does that matter? Well, first, if you've been on Zoom it's been about an hour, so your computer is probably heating up. If it's on your lap, that might be fairly uncomfortable. And even if it's not, it's real overheating electronics just don't perform as well. They slow down, start to become laggy, and make for a not very fun experience. But more importantly, electricity that turns into heat is energy that isn't running your computer. In computers, heat is basically useless. It's not the energy that makes your computer run. So the goal of our experiment is to determine the factors influencing the heat transfer efficiency of semiconductor interfaces in order to develop more efficient electrical systems. So first, this image at the bottom is an image of a semiconductor interface at the molecular level. It's just when two like all things are made out of atoms, and the behavior of these atoms is vital. We're simulating this interface using LAMPS. LAMPS stands for Large Scale Atomic Molecular Massively Parallel Simulator. LAMPS is a molecular dynamics simulation software package, and molecular dynamics is just a way of predicting the motion of molecules using Newton's laws. So across the simulations, the properties of the atoms are changed in order to understand what factors affect the heat transfer efficiency. In the simulations I started running this summer, the property of the atoms that I changed was the mass. So now I'll go back a little bit to semiconductor interfaces. I showed you that picture at the atomic level, but that doesn't really explain what it is if you saw it in everyday life. But it's really easy to look at this picture on the top and understand what's happening. Basically, in the simulation, you have a hot semiconductor on the left and a cold semiconductor on the right. You can also see this in the graph below. It's a numerical representation of a simulation run. While these images are not perfectly mapped to each other, the idea is the same. On the left side of the interface, you're adding heat. And on the right side of the interface, you have a cold semiconductor. The part where there's a huge jump, that's where the two semiconductors touch. That huge jump is not what we want because we're losing a lot of heat. And as I said, when you lose heat, you're losing energy. So what I've been doing over the summer is writing code in Python. The code I've been writing is used to automate the process of creating and analyzing thousands of simulations. At the scale of this research, creating all of the simulations by hand would not only be very tedious, but take a very long time. With writing Python code, I can create thousands of simulations by changing one line of code, and it can create thousands of simulations in mere minutes, unlike the hours, days, or even years it would take to run all of these, to create all of these by hand. I've been writing this code in Visual Studio Code. And writing this code has been the main result of my work this summer. I guess instead of result, I should say product. This code is going to be vital for the work I continue to do, creating more simulations and also analyzing the simulations I've had. So in the fall semester, I will be analyzing the results of the simulations I ran this summer. I will also continue creating simulations, I will continue creating and running simulations, altering different factors of the atoms. I will also begin analyzing this data using different machine learning models. So I want to extend a huge shout out to my mentor, Kirosh Gordiz, the lab professor, Professor Henry, and of course, a huge shout out to Kaylee Allen and Allison Young. Thank you so much for everything you've did over the summer. This summer has been amazing, and thank you so much for all your work. Does anyone have any questions?
Great job, Lucy. Does anyone have any questions for Lucy about the code that she's been writing to study superconductors?
I have a question. What are you looking forward to in the project?
I'm sorry, can you say that again?
Yes. What are you looking forward of like doing in the project? What are you most excited about?
I'm really excited to continue working on creating these simulations. I'm also really excited to start analyzing this data using machine learning. And I'm just really looking forward to getting a chance to do more coding. Coding has been my favorite part about the summer. So I'm really looking forward to continue to do that.
Very nice.
Haley, there's a question in the chat, and I also saw that Matthias raised his hand. Oh, and Mohammed has his hand raised too. So we got some questions queuing up.
Great. So Lucy, Eric left you a comment in the chat. I'm not sure if you see it, but I'll read it to you. He said, hey, Lucy, great work. I know entire labs of MIT PhD students back 20 years ago who could have used your scripts. They were running tons of by hand and manually reading the answers through their codes. So, and I can say the same thing. When I was in graduate school, we used tons and tons of scripts to do just exactly what you're doing. So it's very exciting to see you learning how to do this in high school. And so we have a couple questions. We have one in the chat box that says, what are ways to reduce heat in semiconductors?
Well, that's what our research is looking to answer. That's basically the goal of the research, is to answer that question.
Mm-hmm. And then I know that Mohammed has his hand up, and Matthias, you can follow Mohammed.
Yeah, so great presentation. I remember, like, this is a very important topic. I remember when I was like choosing parts from my computer, I had to pay attention to a lot of the stuff to make sure, like, it wouldn't get too hot, or else, it wouldn't last too long, and with choosing fans and stuff. But yeah, my question was, I remember I think you mentioned using lamps. So I was wondering, like, how was the learning curve with, like, learning lamps and how to use it to turn on, like, the simulations and stuff?
It was a pretty steep learning curve, I would say that. That's one reason I don't have any like firm results, because I had in order to use this, I was spending like a week learning like what is MD, like how do I use this. So yeah, it was a steep learning curve, but it's definitely a lot. It's definitely a lot easier to use now.
Okay, thank you.
And then Matthias, did you have a question for Lucy?
It was really nice work, and I think that's not easy to write this whole automatization. when you have it automated, how quickly do you think you can turn around different molecular configurations so that you can run a big parameter space of atom type or other interactions? How long is it going to take do one simulation run?
So the simulations, the individual simulations don't actually take that long. It's just when you bring it up to scale, it does take a while. So the first round of results, it will be finishing up right now. It took about a week to run these simulations. So the timeline is preliminary results I'll definitely have by the end of the fall term, but it's not magic. It takes time.
And it has so, right? Because you simulate thousands and thousands of atoms. But it's nice that you automate it and that you can now look for inlays and clever parameter tests automatically.
Yeah.
Good work.
Great job, Lucy. Thank you very much. I know from personal experience with my PhD that molecular dynamics simulations do indeed take quite a while to run. So I'm very excited to see your results coming in the fall and the spring based off of all of your hard work on the code this summer. So great job, Lucy. So next we have our returning BEAM intern, Astrid, who's going to give her presentation over the work that she's continued to do this summer. So whenever you are ready, just please unmute yourself and share your screen.
Yeah, so just to start off, am I audible?
You're a little quiet. Not sure if maybe you can turn the, what's it called?
Microphone.
Microphone. There we go. Thank you.
Yeah.
I'm not sure I can do that. Like I'm already on max volume, but I'll try to speak louder.
Is the mouthpiece on your headphones down? I can't see it.
Yeah.
It's down already. Okay, because that's usually why it sounds like that.
So today I'm going to be talking about designing post-transcriptional oscillators in mammalian cells, and I'll talk a bit more about what that means later in the presentation. I've been working in the Weiss lab at MIT with my mentors Noreen Walker and Kathleen Ilya, and I'm from CRLS. So just before we get into the presentation, there's some important terms that will be really helpful to know. First of which is epigenetic silencing, and that's just the silencing of a gene without a change in its genetic sequence. That's often caused by methylation of DNA, and sometimes it can be passed on to daughter cells. Next term is degradation tags, and these are short RNA sequences that recruit deadenylase, and deadenylase is a protein that degrades RNA. So if you have RNA in a cell and it's degraded, then it can't be anymore.
I'm sorry to interrupt, Astrid. Do you mind? You're going to need to project a bit more if we can't, get your mic higher. I just got a message just that it's a little hard to hear you. So we want to make sure everyone can hear you really well.
Yeah, I'll see if I can change my volume. One sec.
It's all of the technology fun we have in the Zoom era. Thank you everyone for your patience.
I think if you go to Zoom and you go to preferences, you can go to audio, and on audio, there is a microphone and an output option. So you might be able to increase it there.
Yeah, is this better?
Oh, but much better.
Great job. Thank you, Astrid.
My Zoom window disappeared.
Did you close out your preferences?
It's not, I'll rejoin the meeting. I'm so sorry.
Were you able to find the window again?
No, it's like the window with the meeting just isn't there anywhere. Oh no, okay. Here it is.
Okay. I was like, oh no. Okay.
So
Perfect.
triplex structures are triple helical RNA structures, and they're used to stabilize RNA that doesn't have a poly A tail. And in translation of DNA, poly A tail essentially keeps the RNA stable so that it doesn't fall apart on its own. And it's really important because otherwise you can't make proteins. And so when you don't have a poly A tail, a triplex structure is the alternative. EndoRNases are proteins that cleave RNA at a specific point, and CRISPR is one example of this. Finally, oscillators are an example, are circuits that repeatedly switch between two states. And so these can be represented by sine waves, for example. And last thing is these two symbols. This sort of sideways T means that whatever is at the vertical end is being inhibited or blocked by whatever's at the thin end. And then this arrow means that whatever's at the pointed end is being enabled or promoted by whatever's at the other end. So the persist platform is what we're using to implement all of this. And it has two domains, persist on and persist off. So the persist on domain, which is shown on the right side of the figure, the way it works is that there are degradation tags at the end of the transcript, and these cause rapid RNA degradation by default. After the degradation tags, if we move along the transcript, there's a triplex structure, which can stabilize the RNA. Then there's the target gene. So if the switch is in the on state, then an endoRNase comes and cleaves the degradation tag, and then the transcript is stabilized by its triplex structure. If the switch is in its off state, then no endoRNase is there to cleave the degradation tag, and deadenases come and degrade the transcript, and the gene isn't expressed. In the persist off domain, the transcript is expressed by default, and when the switch is in its off state, the GCAP is cleaved, and the GCAP it's what keeps an RNA transcript stable from the other end. So again, GCAP is cleaved, the RNA degrades. And what we've been working to design in the past year and continuing this summer is oscillators implemented with the persist platform. And so here we have one example of such an oscillator. There's protein 1 and protein 2. Protein 1 is an activator protein. Protein 2 is a repressor protein. And so in one step, protein 1 activates itself. And then when protein 1 is the dominant protein, it promotes the expression of protein 2. And then when protein 2 is the dominant protein, it represses the expression of protein 1. And so then when all of the protein 1 degrades on its own, there's nothing repressing its expression anymore. And so again, it can be expressed. And so the switch oscillates between two states. So the way we did this project is that we first chose an oscillator motif, and I'll show a variety, I'll show the oscillator motifs that we worked with in a later slide. Identified a set of chemical equations that describe the persist oscillator using the motif that we've chosen. And then, so you can see one example of those equations on the top right. And then we defined the oscillator as a system of ordinary differential equations, shown on the bottom right, and then implemented those in MATLAB and ran deterministic simulations for essentially each protein combination in each for each node of the circuit. This has a wide variety of applications, from understanding natural cellular oscillators that power things like the circadian rhythm to cancer immunotherapy. And the interesting thing about the PERSIST platform is that it's more resistant to epigenetic silencing than other cellular circuit platforms. And so it can be used in stem cells and neurons, unlike these other things. So in the past, I'd worked with my mentors to develop a single post-transcriptional oscillator using the PERSIST platform. And more recently, we examined additional motifs so as to create a more comprehensive overview of PERSIST oscillators. So the motifs that we looked at, we already looked at the relaxation oscillator shown in the middle, and we broadened our search to the Smolin oscillator, which has an additional self-repression on protein 2, and then the Fuseniger oscillator, which is similar to the relaxation oscillator but has an extra protein, and the repressinator, which is 3 consecutive, like 3 proteins, each of which represses the next. So again, it shows an oscillator motif for each one, identified the chemical equations that describe it, then implemented those in MATLAB, and ran simulations to see how it would behave. And our results look like the graph shown on the bottom. For each protein combination, we look at the traces of like the protein concentrations over time. And if they taper off, as shown on the graph on the right, then that's not a stable oscillator. But if they don't taper off, as shown on the 2 graphs on the left, then those are stable oscillators, and we can use them in real-world applications. So we had hundreds of thousands of possible combinations, and of those, only about 600 actually work. The vast majority of those are the Fuseniger oscillator, and then 19 of those are also from the relaxation oscillator. And there's a significant variation in period length, which again broadens the variety of applications that these can be used in. So what does this mean, and what can we do going forwards? We think that the reason the reason there were so few valid oscillators, particularly among other oscillator motifs, is that this is a post-transcriptional platform, meaning that everything happens much faster than on a transcriptional platform. And so we think that if each node is given more time if each node of the circuit is given more time to do its thing, we'll be able to have more functional oscillator motifs. So this project overall helps increase our understanding of natural oscillating systems and has a wide variety of applications, as mentioned earlier. Going forwards, we'd like to implement it in the lab to see if what we've done so far works, and also modify it to enhance its tunability, increase the time at each step to broaden the number of motifs that work, and add the ability to reset the switch, as shown on the bottom right. I'd like to thank my mentors, Erin and Catherine, Professor Weiss at the Weiss Lab, and the BEAM program, including Dr. Kaylee Allen and Allison Young, for giving me an amazing opportunity to work on this project. It's been really fun. Yeah.
Great. Wonderful. Wonderful job. Thank you very much, Astrid. Does anyone have any questions for Astrid about her research? Let's see, do we have any in the chat that maybe I've missed? No. Anybody have their hand up? Oh, Matthias has his hand up.
So this is really cool. The whole genetic circuit design is a super interesting field. And I think working on oscillators is something that from a mechanical engineering physics perspective is really awesome. I was wondering why, when you said you tried so many combinations, only a very few of them worked. I think you had 19 that sort of did the realization oscillator of 587. What's the thing that need to be there for a combination to work, and why did so many not do it?
Yeah, so it's what makes or breaks an oscillator is just the kinetics of each protein. So like if they degrade too fast, then they don't have enough time to have a significant effect on the circuit, for example. Or yeah, so it's kinetics. And so some combinations just don't work well together.
So if one protein doesn't match the time scale of the other one, then the oscillator can never take off.
Yeah.
Okay, cool. That makes sense. Thank you. This is awesome.
Great. And then I see in the chat that Hannah said, awesome job, Astrid. So far, what has been the most interesting part of your research?
I think a lot of the background research has been really interesting because a lot of stuff goes into this, and it's just really cool to see all of it. Yeah.
Great. Very good. Thank you again. All right, so we have 2 more presentations this afternoon. And the next presenter is going to be Mariela Allen-Cadet. So whenever you are ready, please unmute yourself and share your screen.
Okay. Can everyone see my screen? Yeah.
Yes, looks great.
So, hi, I'm Mariela, and this summer I worked in the Shalick lab. And my project is on fluorescence microscopy to evaluate plasma transfection in epithelial cells. And so this is just the breakdown of what I'm going to be talking about. I'm just going to talk a little bit about the project and the greater idea. And then the objective for the summer, introduce some things that I'm going to talk about later, show some images, and then talk about some more things that I'm going to talk about later. And then software is going to be in between 4 and 5. And then I'm going to talk about the specific experiment that I'm going to be focusing on. And then the last thing is just going to be next steps. So the project is, so the Shalick lab is a lab that's based in immunology. So this project is centered around immunology and around epithelial cells. And so the greater idea of the project that my mentor is working on is determining communication between epithelial cells. But to get to that level, you have to have different steps. So there are different pieces that were taken apart, such as what I'm going to be talking about in this presentation today. And so what I'm going to be talking about is a fragment of the larger idea. And so this is a picture of epithelial cells, and epithelial cells are cells that are on the surface of organs like your skin, lungs, heart, wherever, your lungs. And the cells that were used and that you're going to see later in my presentation are mouse trachea epithelial cells. And so for reference, the trachea is right here. It's in your airway. And this is the connection to immunology because respiratory infections affect the airways, and the trachea is part of the airways as well as the lungs and blood vessels, I think. So that's the connection between trying to synthesize a respiratory infection within using these cells that would be affected by the infection. What I worked on this summer, part of what I worked on is which transfection reagent performs the best in a plasma transfection in airway epithelial cells. So like I mentioned earlier, trying to synthesize the reaction of airway epithelial cells, which is why they're being used. And for this particular experiment, it's trying to see how different the data is, and which reagent, which is a chemical mixture, would work the best given the experiment. So plasma transfections. So I'll explain the picture first. So to get DNA into a cell, you can't just put it in there because the DNA is negatively charged and the cell membrane is also negatively charged. So the liposome, which is otherwise known as the transfection reagent, kind of acts like a taxi and picks up the DNA and puts it inside. And then that forms the lipoplex, which allows it to cross over the cell membrane and go to the nuclei. And so some of the examples of the liposomes that I'm going to be talking about in the project are lipofectamine 3000, Fugene, HD, and Bioffect. And an additional part of this project is that these images were taken in 2 different fluorescence channels. And because the mouse trachea epithelial cells were already given a fluorescence encoded gene, it allows a shortcut to occur where you can check to see if the plasmid transfection actually took and how much of the DNA or whatever was brought into the cell actually took to the cells when you look at it in a different thing. Yep. And so the next thing are fluorophores. And so fluorophores, which I'm going to be getting into in the next slide as well. So this is GFP, which stands for green fluorescent protein, and it's expressed in every cell in this experiment because in this experiment, these mice were actually green because their ancestor mouse was genetically engineered in the embryo to have this green fluorescent cells. And also that was passed down to this mouse that was used for this experiment. And then M-cherry will be expressed in the cells that receive the plasmid. And that's going to be the way that it's going to be checked to see if the plasmid transfection actually occurred. And so this is a picture of M-cherry. And this is M-cherry's, this is M-cherry's potential emission wavelengths. And then this picture is M-cherry's potential excitation wavelengths. And this picture is this is the potential emission wavelengths. And then the next one is going to be the potential excitation wavelengths. And then this is going to be what the 2 look like together. So this is GFP, which is the one that I just showed, which was the green one. And this is what M-cherry would look like. And so the filters just kind of provide a narrow window for the light to filter through that only allows in the light that corresponds to the fluorescence gene or the fluorophore that's needed. And so, yeah, so to reiterate, this is the GFP, and then this is the M-cherry protein. So these are the cell images, and these were the same image, or sorry, the same well that was imaged in 2 different channels. So this is the result of the green channel, and this is just like the regular cells that were there. These are all the mouse trachea cells here, and because they're already green, they're all going to show up in the FITSI channel. And then after the plasmid transfection was performed, you can image, well, so this is both after, and so to check to see if the plasmid transfection took place, it was imaged again in the red fluorescence channel. So these are the same well, but 2 different fluorescence channels. And this is proof that the plasmid transfection actually took place because it was encoded with the M-cherry gene. And so the taxi, essentially the liposome, brought over the M-cherry gene into the cell, and it's determining whether or not the liposome was able to break through the cell or not, or if it was able to break through efficiently and deliver most of the whatever was inside the liposome. And so as you can see here, there is some things, and these are a lot of cells actually. This was a really good well, a really good condition. And so next image. So software that I used Cell Profiler, which is like a cell analysis. It's used for microscopic pictures. And then from Cell Profiler, I took the images that were analyzed in that, and then I brought it to Pandas and Jupyter Lab, where I made it into graphical DNA or plotted it. So basically the images go into Cell Profiler because those are just images that were taken from a microscope, and then those images are brought into Cell Profiler, where they are going through a bunch of different procedures to find out how many cells are here and what kind of things are on there. And then that is moved into Pandas after it's gotten numerical data, and that numerical data is transformed into graphs. And this is a specific experiment design. So these are the conditions for the experiment. There are 12 different wells here. And like I said earlier, each of the wells were imaged in 2 different fluorescence channels. And so there are 2 different variables here. The transfection reagent and the amount added. And so like I said earlier, lipofectamine 3000 was 1. And then lipofectamine 3000 with the addition of P3000, which is an additional reagent. And this is supposed to be used to push it closer to the nucleus. And then there's also ViEffect and Fugene HD. And then the amount added, there are some higher numbers here like 0.4 and 0.6 and 0.4 again, 0.3, and then some lower numbers like 0.15. And so the main difference is that there's 4 different amounts here, and then 4 different amounts here, and then 4 different amounts here, but within these 2 different categories. So there's a breakdown between the transfection reagent and the amount added to see like whether a higher amount would matter or not with the same transfection reagent. So this is another concept introduction to image analysis. So these are some screenshots from Cell Profiler. And like I mentioned earlier, so these images that were taken by my mentor, Sam, were given to me. And then I built a pipeline where I made, in this one, there's 9 modules, but in the very final one, there was only 3 because I had simplified it to just identifying the objects and then measuring it. So Cell Profiler is used for microscopic images. And so additionally, what it does, like I had mentioned earlier, it turns these images into numerical data after showing you and identifying what you're looking for in these images. And then from there, those images are taken and processed to be data analyzed and created into a visual form like a graph or a plot or something like that. And so in this image, I have what the identified primary objects module looks like. So this was the original image that was taken on the microscope. And this is how many cells it identified in this one image. And so you can't really see it, but I'll read it for you. So the number of accepted objects, which is basically the cells, is 745. And it identified these cells based off of the parameters that I gave it. And I said that I wanted the cells to be between 20 and 50 pixels. And so cells that were between 20 and 50 pixels and were the right intensity were chosen to become, or chosen to be identified and called FTSE cells. And this is just the outline of what it looked like. And then all these purple things here are the objects that were discarded and not thought of FTSE cells. So they're marked as purple to signify that they are not in the parameters that I had wanted. And so all of this box here, and then all of the data from each image set, and there's 12 image sets, so it's like this times 12. All of that was taken and put into this huge like 12,000 row spreadsheet in Excel with the export to spreadsheet module. And so then from there, I took that and I simplified certain parts of it, and then I brought it into pandas, like I had said earlier, and turned it into graphical DNA. And oh my gosh, graphical data. And so that is basically just to kind of simplify the process rather than looking through like thousands of rows and just having the data there in like one singular spreadsheet where it can be put into a smaller graph. And so here are the results of the plasma transfection experiment. So as you can see, well 4 is like the highest one here, and then well 3 is like second best, and then well 7, 8, and then 12 is like the last. But all of the rest of them had either none or very, very small amounts that they didn't even make it on this graph because of the y-axis being adjusted for the highest result, which was 4. So as I said in the plasma transfection experiment design, well 4 is the combination of lipofectamine 3000 and P3000 at 0.3 microliters. And so this was the optimal condition. And so you want to figure out why it was the optimal condition. So it was based on a combination of the amount and the transfection reagent, which can be shown because well 3 also had lipofectamine and P3000, but it only had 0.15 microliters, whereas 7 and 8 and 12 had 0.4, 0.6, and 0.4 microliters respectively for each. So it's shown that while they did have one of the two that would make for optimal conditions, it didn't make them like the best because they only had the amount and not the transfection reagent, which shows that the addition of P3000 could be more influential than previously thought. And 1 and 2 were just plain lipofectamine without the P3000, and they're not even on this graph. And that could prove to be that P3000 not only blew like everything else out of the water, but it blew the other things that were most related to it out of the water as well. So what's next? This project is still like very much in progress. So there's still going to be a lot more taking of images and then image analysis done in Cell Profiler and ImageJ. And then from there, those results from Cell Profiler and ImageJ will be taken and put into pandas, where they will be put into a graphical form or put into a different form. And so then from there, to answer those questions that were coming up with this experiment and with other experiments, and also to ask more questions like, what does P3000 really do if it's affecting the data this much? So, yeah. And then acknowledgements. I'd like to thank Dr. Kaylee Allen and Allison Young, and my mentors Sam and Mike, and then the Shalick Lab. And yeah, thank you.
Great, wonderful job. Very well done. Do we have any questions for Mariela?
Don't be afraid to put them in the chat.
I was going to say, I'll ask you a question. So the transfection agent, is that what you added on like the 3rd and 4th wells, right? Are you going to add that to other wells as well in order to see if it influences or affects the results?
In like future experiments?
Mm-hmm.
Yeah. So the purpose of this experiment, I guess I forgot to mention that, was to figure out which one would be the best for future experiments. So after doing this one, it's discovered that well 4, which was lipofectamine 3000 and P3000 at 0.3 microliters, is the best one. Mm-hmm. So that would be used in the future experiments.
Cool. Very cool. Matthias, I see you have your hand up.
I do. Mariela, nice work. The transfection agent was the P3000, right?
Yeah.
And you're saying you're going to look more into why this is making this so much better in the transfection. Do you have a speculation what that agent does? Does it sort of do something to the lipid bilayer of the cell to help the liposome to go in, or?
I'm not actually super sure because they kind of keep everything under wraps. But when I was doing some research on what P3000 does, the company that manufactures it said that it helps to bring it across to the nucleus faster. And the image that I used for the plasma transfection explanation actually had P3000 in it, but I skipped over that part because I didn't want to ruin the surprise of like which one was the best. But P3000 was like engineered to help push it faster, but I'm not really sure why yet. And I'm not sure if I ever will know why.
Well, and the company keeps it a little bit of a secret.
Yeah.
I see in the chat that Sam actually said the next transfection is Sunday and that he's going to use the conditions that Mariela identified. So that's pretty exciting. Very cool. Okay, well, thank you very much, Mariela. That was wonderful. I'm excited to see the progress as we go through the fall and spring terms. So certainly not last or least, our final presentation is going to come from Erin. And whenever she is ready, she can share her screen and unmute herself.
Hi everyone, my name is Erin Kim, and this year I have the amazing opportunity to work with Professor Ming Gao's lab under the mentorship of Yulong Han and Wen Hui Tang as part of the Department of Mechanical Engineering at MIT. In this summer, I studied cell packing on spheres through simulation. So I wanted to start off by bringing to attention the really fascinating details in the nature around us. And I wanted to give a few notable examples, which include the hexagons and honeycomb, the spiral on shells, and the center of sunflowers. And I just wanted to say, I've always wondered what causes the specific arrangement of geometric patterns. So from my work this summer, I was able to learn that these structures are formed by the organization of cells in migration and packing. So migration and packing are collective behaviors within the cellular system. And cell migration in particular is when cells have a method of directed movement in response to some kind of chemical or mechanical signal throughout the body. And while this can be done by either a single cell or group of cells, my project is especially interested in the collective nature of cells and the networks that are established between the various cells when they move together and interact with each other. And there are a lot of different real-life applications in which this understanding of cell-to-cell networks can be used for, and this includes improving wound repair methods, developmental enormities, and cancer. For instance, pictured here is a depiction of wound closure through the collective migration of cells over time. So in these different migratory behaviors, cell shape plays a really critical role in this regulation. So as shown in this graphic, during movements like cell division, when one cell divides into two cells, the cell shape changes. And you can also better define cell shape by counting the number of neighboring cells. So here, one cell that originally had 6 neighbors split into 2 cells that each now has 5 neighbors. And it also results in other cells next to them varying their neighbor count as well. And cell shapes can be a variety of different polygons, anything from triangle to a dodecagon, and especially out of them, hexagon-shaped cells, which have 6 borders and therefore 6 directly neighboring cells, are the most commonly seen cell types. So what's interesting here is that when I go back to my project introduction, it's also consistent with what can be seen in nature through honeycomb. And kind of related to this, I came across an interesting series of architectural structures, and it's named cell packing structures, and they're modeled off of these cell packing processes. So as you can see, hexagon patterns are kind of like a reoccurring theme in many of them. And these structures also feature other types of polygons like the rectangles in the top row. And I thought this is definitely like an interesting blend of science, math, and art, and especially finding kind of like an innovative method for building efficient, stable, and aesthetic structures. So given this correlation between cell shapes, packing patterns, and collective cellular behaviors, My major focus of this project has been on counting the number of neighbors of particles in order to then be able to plot and analyze results based on these different polygon shapes. The method that I use to do this is called Voronoi tessellation, which is done by drawing perpendicular bisectors stemming from center points, which are indicated as black dots in this diagram. And then it extends the lines joining these two stations. So once these Voronoi diagrams pile up and then create a much larger scale pattern, it would look something similar to this diagram on the right, which is kind of more packed. And to perform Voronoi tessellation, I use MATLAB. So I started by randomly generating particles on a unit sphere. And this position was initially generated in polar coordinates, so I would then have to convert them to Cartesian. So then through Voronoi tessellation, I would get the shape of the particle on MATLAB. And then in order to get the plots in different packing behaviors, I varied the particle numbers that I inputted. So once you run this MATLAB code, you would get simulations like these two diagrams. And these are just two examples of the results that I got. Especially the first diagram is generated when you input the particle number 11, and the second is when you input 900. So it's made up of 900 particles, and it's rotated to show kind of like a clearer view of the whole sphere. So as shown in these two figures, you can see that higher particle numbers result in more spherical models. So in both figures, the black dots represent the centers of each particle, and then the particles are color coded based on the number of neighbors it has. The sidebar to the right shows, for example, particles with 6 neighbors are indicated in white, and then particles with fewer neighbors, meaning between 3 to 5 are red, and then particles with more than 6 neighbors are blue. So by looking at the diagram, you can really like easily spot trends in which cells of similar numbers of neighbors like packed together, and it's not really as visible to the naked eye than when you see through this diagram. So it's really helpful. And then after running a bunch of these simulation models and then inputting like a lot of different particle numbers, I created this plot that shows the analysis of polygon fractions relative to the particle numbers. So the polygon shapes of each cell are indicated in different color dots. So as you can see here, 3-fold indicates a triangular shaped particle, and then 6-fold indicates a hexagon shaped particle. So here on the x-axis, you can see that I ran many different particle numbers ranging from 0 to 1000. And then the y-axis is the polygon fraction, and that basically indicates the percentage of these polygon shapes that occur in each simulation's particle number. For example, if you look in like this top row, you can see that the hexagon shaped particles tend to make up around 0.3 out of 1 or 30% of the particles, which is pretty consistent throughout the different particle numbers that I generated. And this proves my earlier point that hexagons are the most common cell shape because there are no other polygon shapes that generally exceed this 30%. And you can also see that some polygons are increasing as the particle number increases. So if you look at the octagon in like red dots and then the hexagon in blue or the heptagon in turquoise, you can see that it first like increases and then kind of levels off. But you can also see like an opposite trend where the pentagon in yellow or the rectangle in like green or the triangle in gray, they first decrease and then level off. So these two trends can be seen because the simulation isn't exactly the same as cell packing. And so triangular and rectangular shapes are more common in lower cell numbers, so up here. And then this is why gray and light green dots initially start out as pretty like high in the graph. But then once you generate more cells, the hexagons and heptagon shaped cells get higher in number. Another finding you can see from this plot is that shapes with more sides, for example, the nonagons and decagons, are much smaller in percentage of particles compared to other polygons. So that's this blue ellipse at the bottom. And they're much more like smaller in percentage of particles compared to these other polygon shapes. So that means that by the time it gets to decagons indicated in purple dots, like right near that 0 point, you can see it's almost near the x-axis. And this shows that polygons with more sides than the decagon are really unlikely to show up in these like simulation models, while polygons that have close to 6 sides make up the majority of the particles. So in summary, the focus of my project this summer has been to analyze cell shapes and packing patterns by performing Voronoi tessellation on MATLAB. And then my next steps for the upcoming term is to add standard deviation to my plot that relates polygon fraction to the particle numbers in order to get a better statistic of the data, and also to compare the hypothetical data from my particle packing simulation, which looks something like this left diagram with hexagons, with cell packing, which is a more realistic but less clear-cut polygon shape image you can see on the right. So as I conclude my first term of the program, I want to acknowledge the awesome people who have continuously supported me. First, I would like to thank Professor Ming Gao for giving me the wonderful opportunity to work at his lab, as well as my mentors, Dr. Yulong Han and Wen Hui Tang, who has guided me with such kindness and encouragement throughout this term. And I would also like to thank Dr. Kaylee Allen and Allison Young of the BEAM program for making every intern meeting so enjoyable and memorable. And last but certainly not least, thank you everyone for listening.
Wonderful job. Great job, Erin. All right. So does anyone have any questions for Erin? Oh, I see Mohammed's hand went up real quick. So we can start with Mohammed.
Hello, that was a great presentation. Good job. I was wondering for like the simulations you ran, how long did it take? Like, were they did it take very long? I remember for one of them was like 900 particles. So I was wondering, like, is time like an important factor? Like, does it affect your test a lot? Or yeah, how does it
this is kind of like a glimpse of the code that I had to kind of output these different simulation models. But basically I was able to input like each particle number. So if you just change around like n equals like a certain number, you would just get that shape. So it wasn't like too, like it didn't spend like too much time on like creating those 900 particles. But since I had to generate like from 5 to all the way to like 1,000, and also kind of have more points towards the beginning to be able to spot these trends more clearly, I guess that kind of took time, but not necessarily too time consuming for like generating the specific 900 particles. But yeah, it was a really cool experience in being able to kind of use that MATLAB code to plot like really cool data points.
Thank you.
We have a question in the chat box from John. John would like to know, do you know why some polygons are dominant?
Yeah, so hexagons that I mentioned are like dominant because they have like minimal free energy, and that's why it's like kind of the most stable structure out of all the polygons. So that's something that like the polygon shapes want to kind of go back to, since it's like the most consistent shape. Yeah, and as I mentioned, I thought it was really cool how it's like also present in nature through like honeycomb and yeah, just like those naturally like self-organizing structures.
Very cool. And so I saw that you had mentioned in your future directions that you're going to start taking the code and the things that you're learning with the shapes and applying it to cell packing. Can you describe a little bit more what you think you're going to be doing with the cells and how you're going to and what you're going to learn from them?
Yeah, so my sense of it is that I think it would be like real life experiments that I guess my mentors would get from the lab, and then being able to analyze it in something like a similar method to what I have done this term. But I guess it would be much more complicated in a sense that, you know, since like the polygons that I've analyzed so far are like really kind of clear cut, and you can see that these are like 100% hexagons, whereas these ones are kind of more ambiguous and you can't really tell like what exact polygon it is. So I guess that technique of being able to count the cell neighbors are pretty helpful in here. For example, you can see like this one has 6 neighbors, like 1, 2, 3, 4, 5, 6. So I'm really looking forward to kind of applying the techniques that I've learned this term to, I guess, a more advanced experiment in real life for next term.
Great. And then we will wrap up with Matthias, followed by Sam.
My question is more of a comment, but I really like your slides. They're very clear and easy to understand. And the way how you present your data, how you explain it and how you interpret it is something to take as a role model.
Thank you so much.
Well done. Well done.
Great. And then Sam, did you have a question or a comment?
Yeah, I do have a question for Erin. it seemed like in your model, there was no real lower limit on how small a cell could get. And I'm not sure if that's consistent with like cells growing in a dish, because they can only smush to so small until they would like maybe die. So I was wondering, like, have you considered revising the model to put a lower limit on how small the cells could become?
I haven't really like considered that yet because I've been kind of randomly generating like particles on MATLAB, and I guess it's been kind of a more like virtual like simulation model rather than like a real life cell. So that's kind of what I'm going to focus on next term. Thank you for bringing that point up.
Very cool. Well, in the interest of time, because we are a little bit over 4 o'clock, I just want to take a moment and give everybody an opportunity to give one last round of applause to not only our interns who presented today, but to also all of our mentors and faculty advisors. Without all of you, this program would not be what it is. And so with that, I will say thank you very much, everyone, for attending. Our interns and mentors will resume the program this coming fall. So we take the month of September so everybody can kind of get reacclimated with going back to campus, because we at MIT are returning to campus in September, and our interns are also returning to high school. So the month of September is going to be sort of an adjustment period, and then we will pick the program back up at the beginning of October. And the status as to whether or not the interns will be coming to campus at MIT is still a big question mark. So as soon as we know what the fall term looks like, we will certainly make sure that all of our interns, mentors, and faculty advisors are made aware of the situations as well. But with that, thank you everyone for joining the program and for listening to our fabulous interns talk about their 10-week summer experience.